Einstein theory of general relativity, then the field equation, and the comparison between these two theories in the conclusion. So first, to know about the general theory of relativity, we need to go through the previous theory, that is Newton theory of gravitation. So we all know that the force is directly proportional to the masses and inversely proportional to the distance between the two masses. So actually gravitation is the oldest force known, but it is least explored or least known in detail. Actually the Newton's theory explain the motion of the planets or celestial objects and the behavior of projectile on Earth in a good way. Even though we can see many limitations in this. Let us see that what are the limitations. So we are now that Mercury's orbit keeps on changing like this. So this is one step, like so it goes around like this. But the Newton theory of gravitation did not explain why it is happening like this. Many assume that there are other celestial objects or some other planet near Mercury, but it is not true. We have no proof for that. And Newton's theory of gravitation did not explain the bending of light, right? So this was experimentally observed during the solar eclipse. So this is the actual star position. Here it is Earth, but we see the star position in this location during the solar eclipse. And Newton's theory of gravitation failed to discuss the behavior of gravity in the extreme condition. So that is near black hole, and it is during the beginning of the universe, that is Big Bang theory. So to understand correctly, we need to understand some basics. So in the Euclidean geometry we can see that sum of the internal angles is equal to 180 degree, and we know that parallel lines never intersect. So if we consider this as a two-dimensional thing, and if we curve this, then we will get three-dimensional space. So this is how the universe is. I mean, not this much, but still I am explaining. So this is how we get three dimension. So in this three dimension, we see that parallel lines can cross or diverge. So that means it can intersect or diverge, and the sum doesn't equal to 180 degree. I hope you got this point. In the same way, so if we curve the three-dimensional space, we are going to get four-dimensional. So this is just we can't imagine the four dimension directly. So I gave the example of two dimension, next three, next from 3 to 4. So if we curve this three-dimensional, we get four dimension. It is a bit harder to imagine that. So after 200 years from Newton's theory of gravitation, so there was a problem in the Newton's theory of gravitation that the question arises like two masses are there is no connection between them, how the force is exerted. So it can't be, so if I want to push this, I had to test this, but for those two heavy masses there was no connection. So it was not explained in the Newton's theory. Even Newton can't digest his own theory. So after 200 years, Einstein come up with a new theory, that is general theory of relativity. So in this he explained, okay, these are the things we are going to learn in the general theory of relativity now. So the concept of space-time, curvature of space-time caused by mass and energy, and we will try to visualize the space-time curvature.
Visualize ಮಾಡ್ತೀಯ ಅಲ್ವಾ
ಸರ್? ಅದೇ ಇವಾಗ 2D 3D ಹೇಗೆ ತೋರಿಸ್ತಾ ಇದ್ದಾರೆ ಅದೇ ಥರ ಇಲ್ಲಿ ಟ್ರೈ ಮಾಡಿ ಸರ್. So Einstein said that, okay, so as I said in Newton's theory there was no connection between the two masses. So Einstein said that gravity is not some force, but it is a curvature of space-time caused by mass and energy. It is not the result of curvature of space-time, it is the curvature of space-time itself. So here I hope you everyone has seen this demonstration. So keeping a matrix and keeping a ball inside or heavy mass inside, and if we throw the ball in the matrix, then it takes a circular path. So it is how the gravity works. So again, here, see this statement again and again. Space-time tells matter how to move, matter tells space-time how to curve. So I will explain this again in the equation, that is gravitation field equation. So it explains. It explains the follow. So how the light follows the curve path rather than the straight line. So as is shown earlier in the limitations of the Newton's theory of gravitation, we can see this how the light rays bend and how it is absorbed here. Even in my last seminar, I have explained about gravitational lensing due to the dark matter. So by this we can try to visualize it. So as we saw in the first image, the matrix is bent. We have to imagine the same thing in three-dimensional thing, so that at least we'll get some picture of it. So it explains the theory of it explains how it works near the black holes also. Okay, again the same one. So John is an American theoretical physicist said this: space-time tells matter how to move, and matter tells space-time how to curve. So again, I am going to explain this in this equation. So before explaining that, I will compare these two equations. So Newton's theory of gravitation and here Einstein's field equation. So what you see on the left hand side is the analog of force comparing these two equations. And what you see here, okay, so force, this is analog of force, and here G, that is Newton's gravitation constant, and here we can see Einstein's gravitational constant, that is 8 by G by C square. So let us go to the equation directly. So sometimes G mu nu omega is added, that is known as omega is known as cosmological constant, that is 1.1 into 10 minus 52 meter inverse square. So cosmological, okay, so I'll explain one by one. So here by changing the values of mu and nu, that is from 0 to 3, we will get 10 equations, but I am not going to explain all these 10 equations because that is a little complicated and it requires more time, and each equation has its own significance. So as you know, this is time coordinate and these three are position coordinates. So R mu is known as Ricci curvature tensor. So actually how we are understanding this is, so as you can see the curvature here, we are not going to take the curvature, we are going to take the flat surface. That is, if it is like this, we are selecting an infinitesimally small surface that is flat like this. So this is how the curve is. We are considering infinitesimally small surface like this, and R mu, the Ricci curvature tensor says how it is deviated from this. If we draw the vector here, if we draw one more vector here, we can get the deviating point here. So it is explained by R mu, that is Ricci curvature tensor. Then our scalar curvature says that how space is changed and the distance here, how it is changed. It is explained by R, that is scalar curvature. G mu nu is a metric tensor. It tells about the geometry structure of the space-time curvature. Next, as I said, this is cosmological constant. It explains about the presence of dark energy. So in my previous seminar, I have explained that dark matter is responsible for holding the universe together. But the reason for accelerating of the expansion is dark energy. So it explains about the dark energy, and Yeah, team will explain tensor energy and momentum density. So previously I shown you the code, that is space-time tells matter how to move and matter tells space-time how to curve. So that is here. Matter space-time how to curve. So this equation gives the, if this is unknown, we can get that by this, and this gives the matter how to move. I hope you got my point. So this is how we get only 10 equations. So if we put those tensors in a matrix form, then we are going to get tensor. But we are going to consider only these first off because it is symmetric. So for mu is equal to 0, 0, it has a different significant different the equation sorry that equation have that those all 10 equations are different. So for mu is equal to 0, 0, it is different, 0, 1 different. So you can see the videos related to that because it is not even Einstein took many years to explain this. Even Einstein took the help from many to explain these 10 equations. So these are few points which you can see. So these are the momentum density. Again, here momentum density. So we are writing the first half of the 10. So these are the significance you can get from those 10 equations. So with the presence of new theory, usually we leave the old theory, but now still we are using Newton's theory. There should be some reason to use that, right? So these are the comparison between those two. So Newton's theory of gravitation is more simpler. Yeah, it still works. As I said, it only fails to explain near black hole or near okay, while explaining the Big Bang theory or expansion of the universe. But for general things like projectile motion or something, yeah, this is enough. So why to make life more complicated while have such a simpler equation? So we use Newton's theory still now. So in the presence of strong gravitational field near black holes, we are going to use Einstein's general theory, and Newton's theory is used for the light speed, for the speed lesser than that of the light speed. So it is less complex, and GPS will use Einstein's general theory of relativity. So to conclude that, as I said, gravitation is not just a force, but it is not even the result of the curvature of space-time. It is the curvature of space-time itself. So it is explained by Einstein using that equation. So this revolutionized thought of how to think about the gravitation. First we thought gravitation is some force, but now we know it is a matrix. But still it fails to explain a few concepts. Okay, so again the same word. So what are the holes in the Einstein theory? So it inability to explain the significance inside the black hole. So the similarity inside the black hole cannot be explained by the Newton's special theory of relativity. And in the smaller scale, that is in the quantum mechanics or quantum field, we cannot incorporate the gravity. So it is the main drawback of the Einstein theory. So that quantum gravity came into existence. So there are two promising theories, that is loose quantum gravity and string theory. Still we need to know about the gravitation more and more. Still what we have the theory is very less regarding this. So these are the references.